Let's now consider what we've learned about hydrostatic equilibrium and thermal equilibrium and consider a cartoon view of the Earth's atmosphere. We're going to do this by drawing the Earth. So let's start by drawing a ground level here, and we're going to study the temperature structure of the Earth's atmosphere. So this is going to be our temperature, and here is Z with 0 here at the bottom, ground level. And this is where we live, we people at the bottom of the atmosphere. Now the horizontal axis here is going to be the temperature, because we're going to be plotting the temperature. So I'm going to erase my little ground level here, and we're going to turn this ground direction into a temperature axis. So this is going to be temperature, T, with hot temperatures over here and cold temperatures over here. What we're going to look at is based off of what's called the U.S. standard atmosphere. And this, we're looking at what's called the 1976 version. If you look on Wikipedia, you can find this. And if you search for U.S. standard atmosphere, you can find the NASA and NOAA, NASA and NOAA, National Oceanic and Atmospheric Administration, with one of its 2 headquarters in Boulder, Colorado. The NASA and NOAA report that lays out all the details of the standard atmosphere, which we will only look at the barest features of. So down here on the surface, it's nice and warm. It's pleasantly hot. It's a temperature where water is liquid. And as we rise in the atmosphere, the air gets colder and colder and cools down. And when we reach a temperature of about minus 40 degrees C, we're at a height of roughly 10 kilometers. And at this point, we make the transition from the lower part of the Earth's atmosphere, which we call the troposphere, to the next layer, which is called the stratosphere. And that transition happens at a height of roughly 10 kilometers. Now, the troposphere is quite deep. We live inside of it. Mount Everest reaches just to the very top of it. So here's Mount Everest, just a little bit below 10 kilometers in height. And long distance airplanes, especially like transatlantic and transoceanic airplanes, they fly right up here, right in the lower part of the stratosphere. They do that because in the stratosphere, the air is quite stable and still, whereas in the troposphere, the air is dominated by convective mixing, driven by the diurnal cycle and the release of water and the phase transitions of water and condensation. That convection leads to a well-mixed polytropic profile with an adiabatic polytrope, more or less, for the stratification, which is why I've drawn it as a linear profile of temperature, as we've seen in our solutions for polytropes in hydrostatic equilibrium. Okay, so now we're going to have to go up, and we're going to go up almost to about 50 kilometers now, not quite to the scale. And as we come into the troposphere, something very interesting happens. The temperature profile stops cooling, and it actually starts warming back up. And it warms up to a temperature almost equal to that down here at ground level. I've overdrawn it a little bit here, so let me bring our line back. It warms up to a temperature that's almost the same as the ground level temperature. As as we hit the maximum of warming, we hit what's called the stratopause. This is where we transition from the stratosphere to the next layer up. This marker down here, this layer, this is the tropopause, the place where the troposphere ends and the stratosphere begins. Now, what gets up to 50 kilometers? Well, up to 50 kilometers, this is the realm of the weather balloons with their payloads, and this is well above anything that we can typically fly. The very craziest spy planes and things like that are up at these sorts of altitudes. So let's draw ourselves a crazy spy plane going super fast here with wings, maybe an SR-72 or something like that, flying up at these SR-71, excuse me, flying up at these sorts of altitudes, very high up in the atmosphere of the Earth. Okay, so as we come up in above the stratosphere, as we continue up our atmosphere of the Earth here, now we are up in what's called the mesosphere. And now the temperature starts to decline again, and it gets quite cold again. Now, why do we have this? Why do we have this localized heating? Well, what's happening here is that light from the sun is coming in, and the visible light from the sun goes all the way down through the Earth's atmosphere, all the way to the base, and warms the ground. That's our visible light. But the shorter wavelength light from the sun only makes it partway through the atmosphere before being absorbed. And in particular, the UV light only reaches down into the stratosphere. And that's because in the stratosphere, there's a chemical reaction that happens at these heights where we take O3 minus and we add this to a photon, especially a UV photon, and we get O2 plus O minus, and this is ozone. And ozone is a powerful absorber of UV radiation coming into the Earth's atmosphere, and that leads to local heating in the stratosphere, which causes the stratosphere to be warmer than the layers of the atmosphere below it. This, incidentally, is why the stratosphere has fairly smooth and simple motions. The troposphere has a declining temperature gradient and convection, whereas in the stratosphere, there is an increasing temperature gradient, which leads to a stable stratification. There are gravity waves, but not convection. Okay, now we're up in the mesosphere. What comes next? Well, as we get up to about 80 kilometers, we approach the mesopause up here, the transition of the mesosphere to the next layers. And we have the ionosphere. Is parts of the ionosphere are up in this region. The ionosphere is very important. It's a charged layer in the upper atmosphere of the Earth, and we used it for a long time to bounce radio transmissions. We'd send them up from the ground, they'd hit this, and then they'd come back down at a long distance to do over-the-horizon communication. This ionosphere also limits the radio communications and signals we can get from outside the Earth, so that we have a long wavelength cutoff in the kinds of radio observations that we can do. Well, what lies above? Well, what lies above is that once again, the temperature from a cold point starts to warm up again. And we enter what's called the thermosphere of the Earth. Why does it warm up? Well, up here, again, it's photons from the sun being absorbed, but here it's the X-ray photons that are absorbed and that do the local heating. Okay, now the thermosphere, as part of the atmosphere, it's not a fluid medium that we're really familiar with. Up here, the spaces between the atoms become quite substantial, and many of the atoms are ionized, and we're coming into sort of the plasma environment of the Earth's magnetosphere in the near space environment. And up at an altitude of 100 kilometers, you cross what is called the Kármán line. Let's see if I can spell this right. Kármán line. And above the Kármán line, by conventional definition, lies space. Now, in reality, there's a continuum from very low density thermosphere up into extremely tenuous bits of atmosphere in space. And there is no hard boundary between the Earth's atmosphere and outer space. But you get to 100 kilometers and you hit the classically defined Kármán line. Some other things that we can see in the atmosphere above us, at the kind of mesopause layer, this is where the aurora live. And when you see meteors streaking through the atmosphere, those are also generally up here in the mesosphere. So our meteors live up here. And this is basically the Earth's atmosphere. So going back down to the bottom, we have the troposphere, a convection zone where we live and where all the topography of the Earth exists. We have the stratosphere, where the temperature begins to increase again due to the absorption of ultraviolet light by ozone in particular. And then the temperature begins to drop again, coming into the mesosphere, until it reaches a point where it again heats back up in the thermosphere as X-ray photons from the sun are absorbed and ionize atoms, creating the plasma environment in the near space region around our Earth.